Hello everyone, my name is Lim Shawan and we are from AI2 lecture section, Lab 2C, Group 8, and I'm leader of this group. Today I'm going to present about our project. Our project title is Solving the Farmer, Wolf, Goat and the Cabbage Problem. So for the introduction, artificial intelligence focuses on the development of the system capable of performing the intelligent task through the use of the algorithm and the search technique. Main classical AI problem solving using the state space representation, where a problem is modeled as a set of the states and conditions between them. So in this project, we focus on solving the farmer, wolf, goat, and the cabbage, which is a well-known logical puzzle in the AI. The problem involves the transporting a farmer, a wolf, a goat, and a cabbage across a river while obeying strict safety constraints. If left unattended, the wolf will eat the goats, and the goat will eat the cabbage. So therefore, the challenge is determine a valid and optimal sequence of the action, then safely transfer all the entities to the opposite sides of the river. So in our implementation, the problem is so using the Lisp programming language, we apply the two search methods. So first is the breadth first search as a uniform search. Second is the greedy best first search as a uniform search. So for our objective of this project are as follows. First, we aim to represent the farmer wolf goat cabbage problem as a state space search problem, where each state describes the position of the farmer wolf, goat, and the cabbage. Second, we implement the AI search technique using the Lisp programming language, follow the requirements of the course. We apply compare two different search strategy. First is the breadth first search, which is an informed search method, and greedy depth first search, which is an informed search method. Another important objective is to implement the constraint based on the reasoning. This ensures the unsafe situation, such as the wolf being left alone with the goat or the goats with the cabbage, are always avoided. In addition, we analyze and evaluate the performance of the search method in terms of the solution correctness, path optimality, search efficiency, and the computation behavior. Finally, we extend the greedy depth first search by designing the comparison to heuristic function in order to study how different heuristic strategies affect search efficiency, not expansions, and solution quality. So the goal of this problem is find a valid and optional sequence of modes, then transfer all the entities safely from the starting sites of the river to the opposite sides. So in this problem, a farmer needs to transport a wolf, the goat, and the cabbage across the river using a boat. However, the boats can only carry the farmer at most one item at a time, which limit the possible action. There are important safety constraints that must always be satisfied. The wolf cannot be left alone with the goats without the farmer, and the goat cannot be left alone with the cabbage without the farmer. Any stage that violates their rules is considered unsafe must be avoided. Because the problem has a finite and well-defined state space with clear rules, it can be efficiently modeled as a state space search problem and solved using the AI search algorithm. Now I pass to my team member to explain about the data set.
I'm Lao Sherin, and now I will present about data set description, data features, and representation. To solve the farmer, wolf, goat, and cabbage problem, we first had to define how the computer sees the world. We represented each stage as a simple 4 elements list: farmer, wolf, goat, and cabbage. We use symbolic encoding where W stands for the west bank and E for the east bank. This approach is efficient because Lisp can compare these symbols in constant time, and it keeps the data human readable. For state space analysis and filtering, while there are 16 mathematically possible ways to arrange these 4 entities, many of them are illegal in the context of the puzzle. For example, leaving the wolf alone with the goat is a violation. By applying our safety constraints, we prune the state space down to just 10 valid states, 37.5% of reduction. This is a crucial step in AI because it significantly reduces the number of paths our algorithm need to explore. Data processing, transformation, and operators. Our data processing focus on how we transition between these states. We implemented 4 specific action operators like move with goat or move farmer alone. Every time an action is attempted, the system performs a precondition check to ensure the farmer is actually with the items he is trying to move. We also built utility functions like opposite and specific accessors to ensure the code remains clean and the search remains fast. Finally, let's talk about data cleaning and heuristic. Unlike traditional data science where you clean a static file, our data cleaning happens dynamically during state generation. The saveP function ensures that an unsafe state is never ever added to the search frontier. For our informed search, we transform this symbolic state into numbers using heuristic like H1, which simply counts how many items are left on the starting bank, and H2, which provides a more advanced estimate of the trips required to reach the goal.
Hi everyone, my name is Nguyen. Now I will present about the searching method that we use in our project. For the first method is breadth process or BIS. BIS explore every possible move level by level using a cube. We choose it because it always finds the shortest path. For this puzzle, the optimal solution is only 7 moves and BFS guarantees we get it. It is reliable for small problem like this. The second is pretty best process. It uses a heuristic to choose the state that looks closest to the goal. We create 2 heuristics. H1 counts items on the website, and H2 estimate the minimum trips needed. Greedy is usually much faster than BAS because it tests fewer states, but it may not always give you the shortest path. This let us compare the best path from BAS with the faster path from Greedy. Now I will explain the main function, starting with the basic ones. First, we have step representation functions like mistake, farmer side, wolf side, god side, and camel side. They create the states list and let us easily read its position. This makes the code cleaner and reduce errors. Next, the opposite function switches the size from west to east or east to west. We use it in every move. Then, the set P function checks if the state is safe. It makes sure the wolf is not left alone with the god and the god is not left alone with the cabbage. This is a very important filter. Then, the for move function, which is move farmers along, move with wolf, move with god, and move with cabbage, creates new states for legal moves. They only allow moves when the farmer and items are on the same side and the result is safe. This defines all the rules of the puzzle. Next are the functions for generating states and guiding the search. First, the success function tries all four moves and return only the safe and valid states. Both BFS and British search use this function. Then we have 2 heuristic. Heuristic 1 simply count how many items are still on the website. A lower number means closer to the goal. Heuristic 2 gives a better estimate. It returns 0 at the goal, 1 for 1 item left, and 2 times n minus 3 for 2 or more items. It considers the farmer return trips and usually works better. The select heuristic function let the user choose between S1 and S2 easily. This helps us test and compare them without changing the code. Finally, this function runs the search and show the result. First, the BFS solution runs reverses. It explores level by level, avoids repeated states, and counts expanded node and QSite. It always finds the shortest solution. Next, the greedy solve functions run greedy best versus. It picks the state with the lowest heuristic value and track nodes and opposite side. It shows how a good heuristic save time. Next, the state description function creates clear sentences like farmer takes go to east. Then the print part function shows the full solution with number step and mock description. Last, the compare all function run all 3 versions, which is BFS, greedy with S1, and greedy with S2. It measures time, space, not expanded, and part length, then display a comparison table. This is our main way to evaluate performance. Now, let's try to demonstrate our coding. We open our article CL, then we load the file. We can type this command, load. Then we can either copy paste the file part name or enter file name. Then we enter. As you can see, the output is T, which is true. That means we successfully logged the file. Now let us try the function. We solve our puzzle solution with BFS. Enter. Now you can see the BFS solution is come out. total 7 steps, and this one is raw practice. Now we solve with greedy resources, then enter. Here you can see we got solution H1 and H2. H1 is simple count heuristic and H2 is minimum trip estimate heuristic. And here we need to make sure we are choosing one or two from this selection. If we enter any character or symbol like this with that character, okay, invalid input. We try again for a symbol, okay, also invalid input. So we need to make sure we type one or two. Now I type one, enter, the solution come out. Now we try again, solve with greedy search, enter. We have to select. This time I enter H2, enter. The result is come out. And the last thing, when we want to compare all the functions performance, we can enter compare all, then enter. As you can see, the comparison table is out now. It compares the three methods with measures time, mass space not expanded, and path length.
Finally, for our search hyperparameters, we choose a strategy design decision over the numeric values. We implemented the BFS using the FIFO grid to ensure we find the shorter path. For our informed grid search, we developed two heuristics. Heuristic 1, a simple count of the item on the starting bank, and heuristic 2, a more complex formula that accounts for the farmer's return trips. By keeping the operator order fixed and the state space limits, we ensure our performance metrics like node expansion and the time are fully reproducible.
Hello everyone, my name is Lim Ensi. Now I will introduce accelerometer setup and key performance result. All experiments we conduce in a controller list environment running on an Intel i5-1335U system with 24 GB of RAM under the Windows 11. This ensures that our measurements are consistent and reproducible. The algorithm we evaluate based on the three main criteria: completeness, optimality, and efficiency. Efficiency is measured in terms of execution time and the number of nodes expanded. For the result, we can see that BFS then 0.017 seconds and expand 10 nodes to reach the 7-step optimal solution. Both greedy H1 and H2 complete in only 0.002 seconds and expand the 9 nodes, which is the approximately 8 times faster than BFS. Memory usage is minimal for all algorithms due to the small state space. At this stage, we are simply presenting the quantitative difference, with the resulting behind this difference will be discussed on the next slide. Now, we analyze the search behavior of this algorithm. First, both BSS and greedy achieve the 100% completeness and fit the optimal 7-step path, which confuse the correctness of our implementation. The main difference lies in efficiency. Greedy search guided by heuristic knowledge complete the test faster and expand the filling node. In contrast, BFS explores all steps level by level without guidance, with each the less efficient. Looking closely at the step 3 in the solution part, this is a clear behavioral difference. BSS choosing to move the cabbage following strict level order expansion, while greedy move the wolf, selecting the standard mode processing by the heuristic. Regarding heuristic, H1 and H2 perform identically in this dataset due to the small stand spec. However, in light of the move complex problem, this heuristic can learn to different search path and efficiency outcome. So, this analysis shows how heuristic influences decision making during the search and why informed search can improve performance without sacrificing correctness. In our conclusion, this project demonstrates that informed search improves efficiency. Critic search guided by heuristic complete the search faster and explore fewer nodes compared to BFS. At the same time, BFS guarantees optimality, ensuring that the solution found is the shortest possible path. Although H1 and H2 show the same performance in this small dataset, heuristic become critical in launch of more complex problems, where they can significantly affect efficiency and search path. Looking earlier, future workload include implementing a search and scalable system whereas to maintain both efficiency and optimality while handling more complex scenarios with more entity or dynamic constraints.
Overall, this project confirms the connectedness of BFS and grid research, highlight the role of heuristic in creating search efficiently, and provide a foundation of future research in intelligent search strategy. So this is our group presentation. Thank you for your listening.